All right, I think that's everybody. Is anybody still coming in? Noises?
Jonathan says he's on the way.
Okay, John's on the way. Other John is here. All right. So today is day 10. We lost a day to the storm. Did everybody make it through the storm okay? No major calamities? All hail the mag lab. I mean, that's 3 hurricanes in a row that have done the same thing.
Mm-hmm.
And I understand the energetics, but I also understand why everybody's saying
I'm
all hail the mag lab.
Maglab-filled. I'm Maglab-filled.
Right.
Like, I believe it.
I know, right?
I'm starting to believe
I know. So, okay, so we should probably I should probably make you guys actually work out how much energy is actually in a hurricane so you can see how vastly large a hurricane is compared to anything that the MagLab can do. So I'm going to probably try to cook this up into a homework problem when we get to magnetic fields, because that's pretty perfect. So anyway, when we get to magnetic fields, if we get to the end and I haven't gone over why the MagLab can't stop hurricanes, let me know and I'll try to remember to do that. I don't have anything pulled up right now, so it's not already in my list of crap to do. Yeah.
Could we do something to the MagLab to make it, like, more equipped to somewhat deal with the hurricane?
No, because I mean, there's like 6 orders of magnitude in the energy differences. So the hurricane is so much larger than anything that we have the capacity to produce as human beings. I mean, the biggest punch we have are large nuclear explosions, and even those are 6 orders of magnitude too small to affect the actual hurricane dynamics. So, because I mean, the hurricane is the size of the whole state of Florida.
That's crazy.
Like, think about, like, you look at these maps, it's really like, when it makes landfall here, when the eye makes landfall, it's already hitting Atlanta. This storm stretched from St. Louis to Washington, D.C. I mean, these are such vast, mind-bogglingly big objects. So anyway, we'll talk more about those. And I usually cut out the rotational dynamics section because there's only so much you can do, but there's a good section on rotation, on hydrodynamics in a rotating frame that helps to explain why hurricanes form the way they did. I'm pretty sure I got the sign of the rotation of the hurricane wrong when I did it real quick the other day. Hurricanes rotate counterclockwise, whatever I said in the last video. Okay, so let's talk about reading questions. So there are 2 readings due during this storm. Thanks for getting your readings done, even though there was a storm going on. I appreciate that. And for the future, if there's a storm and there's a reading or anything due when there's a storm on, I'm going to leave the assignment up just to see how it does. But if you can't make it, that's okay. I'm a reasonable human being. Okay. Boom, 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 boom. So I'm just going to run through the questions just to make sure we fix all the things. So several of you had asked, and I forgot that he did this because it's at the end of this section, and I forgot it was there. So a couple of you had asked about the Cowling approximation, and I was like, Cowling? We don't get to Cowling until chapter 15. But there's another Cowling in this section, and what he says, the book is actually kind of vague and not very helpful. So what he says is that V of R and T and theta and phi equals, so what we had done was we said dV dt equals minus gm over r squared minus grad p 1 over rho grad p. Okay, so we said this is the acceleration, this is gravitational force per unit mass, this is the pressure force per unit mass. This is just Euler's equation that we've been writing up a whole bunch. So we had taken this as a function of just radius alone. We had ignored the theta and phi components and just said the whole thing is going to either oscillate or collapse. And that all comes down to the sign of gamma through some math. He then goes on to say, well, okay, so radial oscillations are are interesting if it's all moving in one direction, but that's just one of the possible solutions to I have a big thing that can vibrate. How can it vibrate? What are the ways that it can vibrate? So if you've ever taken, if you ever played a drum and watched a drum head really carefully, it doesn't just vibrate up and down in a symmetric mode. There's jitters and things that are still radial but not uniformly radial. So we had said V is a function of radius and time, but now if you say V is a function of radius, time, and theta and phi, so now you've got R, actually let's do it time and then R, theta, phi. This is now a fully three-dimensional problem. And then he writes down this other bit that he says e to the I minus I omega n ln t times, what did he call it, c of n ln of r y ln of theta and phi. And then he goes on and talks about the Cowling approximation. And the Cowling approximation, he doesn't actually say, like he says what it is, but there's no math associated with it. This isn't the Cowling approximation. What this is just writing down how I would say, so when we did sound waves, I said rho 1 of x and t is going to be some amplitude times e to the I kx minus omega t. Remember doing that? Fully in 3 dimensions, if we were doing this in space, so we did sound waves in 1 dimension, but it doesn't really matter, it looks the same in 3 dimensions. What happens is I get a k dot x, and I now have plane waves in 3 dimensions, and I got another one coming out for it. So I've got waves in those 3 dimensions. That's good for Cartesian coordinates, because now I have plane wave, I have an x plane wave, a y plane wave, and a z plane wave, and they're all plane waves. But if I don't have square conditions, then I need to deal for this term, this k dot x, this e to the I k dot x. I can't use e to the I kx anymore if I'm doing something round. I need to use spherical harmonics. So with this expression that he wrote, he's got the oscillating term, e to the I omega t, and then this radial term, which is just c of r, and then the angular term, which are spherical harmonics. Have you guys seen spherical harmonics anywhere? Okay, so you've probably seen them in mech, yes?
Quantum.
And how many of you guys have seen quantum already? Oh, sweet, okay. So these are the same spherical harmonics that you use in quantum, and the reason that you use those is because quantum is really just doing everything in Fourier space. I have decided, for my own inner peace of mind, that that is a tooth and throat singer doing his meditative song as he walks around campus, and that is his meditative om. Because otherwise, I really fucking hate leaf blowers, especially when they're right outside my door. So anyway, so this expression isn't an approximation yet. It's just writing down all of the oscillating terms. Because spherical harmonics oscillate, but they oscillate in roundness. They oscillate around a sphere. And then the Cowling approximation says, okay, you do this, and then you ignore the perturbations in the gravitational potential, and everything's actually easy. But he doesn't go on to actually explain what that does. So, but I wanted to pull this up just to say that this isn't a weird or approximate. It's the same thing that we did here. It's just you have to use spherical harmonics if you've got theta and phi. You can't use e to the I kx. But other than that, all of the Fourier transform stuff that we've said works just fine, because spherical harmonics are another Fourier transform-like thing. Okay. That was a little bit long on that. What is the Schwarzschild criterion? The Schwarzschild criterion is the criterion on the derivative of, so you have temperature as a function of radius, and you have pressure as a function of radius in a star, or in a pot that's boiling, and maybe radius is z now. Actually, we did this in z. We didn't do that in radius. Let's call it z. And we did a bunch of math, and we said that rho star minus rho prime, and remember, we have a little blob, and then we lift it up here, and we have a rho prime, that's the background, and a rho star, that's my blob. So rho prime minus rho star, this is going to tell me if my blob is going to float or sink. And this is going to equal minus 1 minus 1 over gamma d by dz of log p plus d by dz of log temperature. And this has to be bigger than, let's keep it on this board, bigger than 0 for stability. And so the Schwarzschild criterion is just packaging up the right-hand side of this equation. It's just saying we've got some, now we have a statement about the derivatives of p and t. And so the Schwarzschild criterion is that the log of p plus the log of t derivative is all got to be bigger than 0. Now you can rewrite this slightly differently, and you could say d by dz of log t over d by dz of log p has got to be bigger than, less than, and then we put an absolute value on this, which changes the sign of everything. 1 minus 1 over gamma. So this is the Schwarzschild criterion, and this just says, what does the temperature gradient have to be if it's going to start to convect? And if the temperature gradient is too big, then you start to drive a convection cycle. But if the temperature gradient isn't big enough, then it won't convect. Bifurcation. So a bifurcation is a curious thing. A bifurcation is just when the behavior changes. And if you have something that is prone to chaos, then usually there's a regime where it's not chaotic, and you can turn up whatever your order parameter is and make it become chaotic. So for instance, this is how I first learned about bifurcations. If you turn this faucet on so it just drips, if I do it real slow, it'll just drip, 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 and it'll fill up. Like if I have a real slow leak, it'll fill up whatever bubble, and then it'll eventually get too big and it'll fall, and that'll happen at basically the same rate all the time. But if you turn up the rate that your leak is a little bit, then you'll suddenly get chaotic behavior. It will bifurcate into a short and a long phase of, so it'll go drip, 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 drip. So you'll get these higher order modes as the behavior goes from one frequency to two frequencies. And that's usually an indicator of the onset of chaos. Not necessarily turbulence. Turbulence is something pretty specific. Chaos is a bigger set of nonlinearity dynamics, which I'm not going to get into, as fun as that would be. Have you guys done any formal chaos in anything, Lyapunov exponents and that kind of stuff? It's pretty fun stuff, but beyond the course, beyond the scope of what I can get done here. Figure 7.8. Now I forget what figure 7.8 was. Sometimes I write notes about your questions and I'm like, I'm totally going to remember what that is. And then I don't. Oh, 7.8 is this figure in the book. For some reason, my cursor went away from. Where's the book? Oh, it's on my desktop. Crap. I can't remember where I put the book. It's in here somewhere. Anyway, there's this graphic of. I'll sketch it. So there's this graphic of the radial velocity contours, or the angular velocity contours in the sun. So what it looks like is this. And there's numbers like 420 and 440, 400 and 380 and 440 and 460. And so what this says, this is the angular velocity, omega, for the sun, as measured by helioseismology. I'll talk about what helioseismology is a little bit more in a second. Actually, let's do that now. So, helioseismology has really developed an enormous amount since the publishing of this book. They've gone from it being a cool thing where you can watch radial pulsations of stars to really being able to map the interior of a star. Because if I have a star, remember that P and rho are both functions of radius, right? And the star isn't by itself an adiabatic thing. There's a fire on the bottom, right? There's nuclear burning at the center of the star, and that's hot, and there's a hard vacuum on the outside of the star. So it's not at all adiabatic. So the sound speed, remember the sound speed, c sound squared is dp d rho. This changes with depth because pressure and density both change with depth. They both go up, but not in a uniform, nice, smooth way. So if you happen to flick the sun here, if you can just punch it all radially, then it will just radially contract, like all at once. But that's very difficult to do. Things don't actually generally act all around at once unless it's gravity. So if I have to poke it here, there's going to be a wave. And if I poke it immediately at the center and the sound speed is uniform, then it'll just go to the other side. But I'm not poking it immediately radially ever. And the sound speed does change. So remember Snell's law. Snell's law says that a photon will follow the path of least action or is going to bend when the index of refraction changes. What's the index of refraction? The index of refraction is just the speed of light in that prism. So as you change the speed of propagation, things hook around. So I will get, disturbance launched here will actually show up here. And one launched here will show up here. And you have a dispersion relation. Omega equals some complicated function of k, and this is all now radially, so it's all, you got to do it all with spherical harmonics, which is not something that I'm going to get into in this class. But what it lets you do is it lets you get a description of the radial modes that the star can experience, and these are like bubbly, small radial modes, like hair coming off, like things go up and down all over the place. And from the spectrum of fluctuations around the star, you can tell how deep are these waves going. I skipped a bit there. But from the spectrum of disturbances that you can see, you can measure into the depths of the star, which is really cool. I saw a cool talk on helioseismology when I was in grad school, and the guy opened up by saying, in the 80s, we understood the sun really well. And then we developed helioseismology, and we could actually see it, and we stopped understanding it. Because that's how it goes. So anyway, I'm not going to go too deep into helioseismology, but it's the same basic idea. You take the equation of motion and you perturb it. You got to do it in spherical harmonics, and then you get these spectra out. And from these measurements, we can tell how the star is rotating. And so we can see that the top, this is all constant angular momentum here. So the top part is kind of rotating like this. The bottom part is kind of rotating like a solid body, or the interior part is kind of rotating like a solid body. But it decreases as you get towards the center. So it's spinning a little bit faster here than it is here, and it's spinning a little bit faster here than it is up here. So it's not in solid body rotation, except at the very core. Like when you get to the center of it, down here, then it's in solid body, but the rest of it is differential. Now the differential rotation in the sun is necessary to make the magnetic field do what it's doing. So we'll come back to that in a little bit. Okay, so if you have a sample of honey, and it is not just honey-flavored corn syrup. Rumor has it, I haven't actually tried this, you can tell if it's real honey by putting a little bit of water into it and swirling it around and watching the honeycomb pattern arise in the honey. And I'm inferring from the question, but then the assumption then is that honeycomb pattern was imprinted by the actual honeycomb that it was in. And I would be surprised if that's not the lore that goes around it, but that's not what's happening at all. So there's no memory. A fluid doesn't have any memory, regardless of what any homeopathic peddlers of snake oil will tell you.
Mm-hmm.
Fluids don't have any memory. You put something in, you take it out, it's gone. And if you dilute something so that there is less than one particle in that fluid, it's gone. It's not there anymore. But that doesn't mean that this phenomenon doesn't happen. And there's a really cool book, a really cool image in the book, which might have triggered your question. This image here. Oh, what am I recording? I don't want that. Let's put it on me. I'm better. So there's this image here that shows this honeycomb pattern in this dish. And these actually are coming from two different, but still in the same chapter, instabilities. But it shows you something pretty similar, that nature really likes making honeycomb-shaped structures. So when you have a convection cell, so if you take convection that we started convection, but we didn't go into the spectrum of convection cells because I want to do other things. But one very classic thing that happens is this pattern of hexagons. You get a similar pattern of hexagons from the Rayleigh-Taylor. So you're going to have Rayleigh-Taylor moving in 2 dimensions, and when the viscosity of the honey is right, then it's going to set up Kelvin-Helmholtz instability that's going to make a 2-dimensional Kelvin-Helmholtz instability that's going to be set by basically the viscosity of the honey. So it comes from the material properties of the honey, not any kind of memory in it, but it's a Kelvin-Helmholtz instability that is kicked up by the interface. So it has to do with how gluey is the honey will tell you how well it can retain its structure instead of just getting mixed. So a cheaper sugar solution will just get mixed and not actually make that pattern. But that's an interesting question, and I haven't heard that before. Let's see. Non-radial oscillations, where do they come from, and does convection play a role? So we have purely radial oscillations, which are every radius, like all the surface at the same time. But then you also have like oscillating radial, where you have one bit comes in and one bit goes out, and then they switch, just like jumping on a mattress. If you jump on a mattress, your kid brother goes up, provided you've got really springy mattresses. Or have you ever seen those huge inflatable things at various recreational lakes that you can jump off of and make your brother go flying? So there's modes that are radial but not uniform, but then there are also the differential rotation modes. So the differential rotation is tightly coupled to the magnetic fields, but also the rest of the dynamics of the sun. And the convection also matters, because the convection gives you these cells that are like the size of Texas that come up and boil around. So the convection helps make things boil. The differential rotation makes things spin around. And that makes for all kinds of non-uniform modes. Let's see, how precise can helioseismology get? So it really comes down to, I think, the time resolution and the space resolution of the image, and then our understanding of the plasma physics and the plasma state. I think that the plasma state is probably the limiting factor in our actual accuracy, but in principle it can get pretty accurate. But there's a limit to how deep in the sun it can go. Helioseismology only gets you to a certain depth, because all the sound waves just rattle back out. So it can't probe too deep. One of you had asked about recent helioseismology advances. I didn't get a chance to go into the depths. Define convection and conduction. So convection is when the velocity is involved. So convection is a bulk motion of the material, whereas conduction is a molecular motion of the material. And convection goes with Navier-Stokes. But conduction goes with the grad K, grad T term. So it's gradients in the gradient of T, or del squared T. So quickly, very quickly becomes diffusion of temperature. So temperature will just diffuse outwards based on this conductivity. So if the conductivity is high, then the conductivity can go fast. But conductivity is actually a really slow process. So convection wins in, I'm not going to say every case, but every meaningful case, convection will win as a bulk transport because you can just pick the stuff up and move it. There's an old saying, never underestimate the bandwidth of a station wagon full of tapes. Back in the day, before the internet was quite as connected as it was, they used to get the internet to Australia by putting it on tape and putting it on a plane and sending it over there. Because that's much higher bandwidth than what you would have by an actual wired connection in the day. And the same is still true. If I need to move a petabyte of information, I'm just going to go get it. Because you can't transfer that much information, but you can just go get it and bring it here. So, and that's kind of the difference between convection and conduction. Convection is letting the internet stream trickle in, and conduction is going to get the computer and bring it to your house. So depending on how much data you have to move, one might be better. And in reality, if you have a petabyte of data, you just leave it there. You don't want to actually ever move that. Let's see. Oh, oscillations are standing waves. What does that really mean? And what's the fixed thing? The fixed thing is the center of the star. Because this object, the center of mass, is going to be fixed in space. If I flick it, if I do all kinds of perturbations that aren't imparting a bulk motion to the gas, then the center of mass is going to be fixed. If I'm just perturbing it, I'm pulling it up here, pulling it up here, and then my perturbations are fixed, and the center of mass will be fixed with the star. And you can prove that, but I'm not going to go into those details. Let's see, why does the sun not rotate like a solid? Because it doesn't have to. And things are only going to rotate like a solid body if they have to. You have to force it to. So like a galaxy rotates like a solid body because it has to, because of the dark matter. And it's not rotating like a solid body, it just looks like a solid body, but it's not at all solid. They just happen to have these constant rotation curves because dark matter is weird as hell. Okay, so that was the first reading. How am I doing on time? Okay, cool. Yeah.
Do planets like Jupiter also like spin the same way as the sun because they're like gaseous more than they're solid?
That was two questions. They all rotate, everything rotates in the same direction of the sun because the initial planetary nebula had a certain angular momentum and everything fell out of that. So everything is taking away bits of that angular momentum. So, except for Venus, which goes the wrong way. It actually is just going slower than its rotation period. And Uranus, which is sideways, but both of those happen from something scattering. There was some violent event that made those planets rotate the other way. But everything rotates the same way because the initial angular momentum is the same for everybody. That's an interesting question. But planets can't convect, though. Why not?
There's no fire in the middle?
That's right. There's no fire in the middle. There's no temperature gradient. There's nothing that's causing the temperature gradient that's necessary. And remember, the Schwarzschild criterion is a statement about the temperature gradient. The temperature gradient has to be big enough for the convection to start. Planets don't have any fire. There's nothing burning. When you get to a brown dwarf, which is like 15 or 20 Jupiter masses, then they start burning deuterium, which is a much slower process. It's a weaker fire, and there's not as much of it. So brown dwarfs are cold. Okay. What does the Rayleigh-Taylor instability look like? I have a bunch of movies. Would this perturbation work on any amount of fluid? So I'm going to be careful with any, because that means very tiny. So it has to be, the volume has to be large enough that it's still, that the fluid dynamics approximation are still valid. So you can't have like 20 atoms in a box. All of then you have to use density functional theory or quantum mechanics or something more complicated. But as long as you have a macroscopic amount of fluid, then yes, this all works great. Which is actually a very tiny amount of fluid. But when you have a tiny amount of fluid, what quantity of the fluid is probably really small? What's the one property of a flow that we've talked about? Some dimensionless number. The Reynolds number. So if I have a tiny amount of fluid, my length is going to be really small, so my Reynolds number is going to be really small. So all of the fluid dynamics that I'm going to do is going to be using the diffusive approximation. So remember, Navier-Stokes d by dt of v plus v dot grad v equals -1 over rho grad p. I'm going to write that small because I don't care about it right now. Plus nu del squared v. So if the Reynolds number is small, I can throw out this term. And then my equation looks like d by dt of v is equal to nu del squared v. And I have a diffusive process. So, and a lot of interesting things happen when this is the only process going on. When you can throw out the bulk flow and you only deal with the viscosity, then a lot of interesting properties happen. So there's a whole field of study called microfluidics that is basically doing interesting things with tiny little bits of fluid. Anyway. Yeah.
You mentioned about like the sun has, because of the inside a solid body, and then as you go outside the density will change and it has a differential rotation. So the case of Earth would be like basically completely different because it's a solid outer shell that is rotating, and then as you go inwards there will be a part where it will not be rigid body rotation, but then the core at the middle, at the center is almost rigid body.
Yeah, that's right.
So it'll be like kind of symmetric in that sense, where it's a rigid body outside and a rigid inside, and then both of them have rotation, and then there is like a region in the middle where it has some sort of differential rotation going on.
Right, because the Earth, this was explained to me once, and it made perfect sense. I was like, oh, that's so clear and obvious, and then I immediately forgot how it worked. And I have not gone back to pick it up, but the core of the Earth is convective, not because it's burning at the center of the Earth, but because there's an intriguing chemical materials properties process that happens. As iron goes down in depth, it undergoes some kind of phase change and something crystallizes and releases a bunch of latent heat as it crystallizes. So there's this materials property phenomena in the center of the Earth that is doing all of the releasing of all the heat for the driving of the Earth, which is intriguing. So it's not a nuclear process, it's a chemical process.
So depending on the iron content in the core of a planet, we would know if it is volcanically active / just in general convectively active.
I don't know enough about geology to answer that question. In principle, yeah, if you understand the chemical compounds in the core, you could be able to say if it was.
Or vice versa, I guess.
Yeah.
Because that would be more. Yeah.
Let's see. Why is this thing constant? I'll talk about that. Instability is a growing perturbation. Yes. So for all of these instabilities, I'm going to talk about this again when I get there. We're going to have things that look like e to the I omega t. And this oscillates. But if omega, through my math, happens to be imaginary, then I get e. So if omega is equal to I capital gamma, then I plug this in, and this is equal to e to the I plus or minus gamma t. And this is exponential growth or decay. And exponential decay is not very interesting, but exponential growth is interesting. Sometimes exponential decay is interesting, but usually that's not the thing that's going to knock your plate off the table. Um, two questions that I'll get to. What is the significance of irrotational flow? So irrotational flow is basically any flow that's not really strongly interacting with a boundary condition, because we learned from Kelvin's vorticity theorem that the vorticity is basically constant unless you're producing it in some way, and that's got to be either a boundary or with viscosity. So a lot of flow can be treated as irrotational. So a lot of wind in the atmosphere you can treat it like it's not, doesn't have any vorticity because it's just a bulk flow that's moving. And then you can do better math with it. So we like irrotational flow because if del cross V equals 0, then I can say that V equals minus grad phi, and then I can work with this scalar instead of a vector, and that makes my life easier. But it's also a reasonable approximation. There's not a huge, in the room that we're in, there's not a huge amount of vorticity in the air. It's all pretty still, and there's not a lot of swirling action. What are the effects of angular momentum and magnetic fields on all of this? That was my PhD thesis, so that takes me a minute. So it's kind of complicated. So if I thread it with magnetic field, magnetic fields can both stabilize and destabilize things. Rotation tends to stabilize things. So if I make this rotating, then I have a rotating system. And then you'll have Coriolis and centrifugal forces that you have to deal with. And that's harder. But kind of depending on what you're doing, it'll flatten things out. I will talk about that. I will talk about that. How does Jean's instability affect the universe? I might talk about that in a minute when I get there. Basically, the Jean's instability says that the universe has to be expanding, or it has to be finite, or it has to be empty and devoid of mass. We're pretty sure it's not finite, and we're pretty sure it's not devoid of mass, so it has to be accelerating, it has to be expanding, which I'll show you. Okay, any other questions on the questions? So we are going to talk about, what all are we going to talk about today? My notes for this section are not very good. These notes are better. Okay, so what are we doing today? So today we're going to do some two-fluid interface instability stuff. Because it's important, like we talked a little bit about boundary conditions, and now we're talking about what if the boundary is another bit of fluid and can move. So a boundary is a hard wall, but a fluid is not. And yeah, so I'll let Brandon come back to that part. So let's set this up. So we're just going to say I have two states. I have sorry, I gotta get the prime right. I forgot to write down which one is primed and which one is unprimed. Where did you go? Yeah, primed is on top. Okay, so I've got this fluid that has some velocity u prime that's in that direction. Let's call this the x hat direction. Let's call this the z hat direction. And I have some, and it also has some density and pressure, and probably temperature and other prime quantities. And then on the bottom we have u, which is also flowing in the x hat direction, and rho and p. And we're going to make the assumption that we're incompressible, so div v is 0, and we're also just going to go ahead and make the assumption that it's irrotational. We're just looking at some fluid in some space somewhere. We haven't done anything to give it rotation. So we can say that curl of V equals 0. So both of these allow me to say that V is minus grad phi, and I'm going to write this up here, v equals minus grad phi. And also del squared phi equals 0. So I get both of these things from these two equations, from these two conditions. And I know Navier-Stokes, so I know d by dt of v plus v dot grad v equals minus grad p over rho. Okay, that's different from the way I've been writing it. Why? So this, normally I write this as 1 over rho grad p, but now I wrote it as grad p over rho. Why do I get to do that? I've already made the assumption that lets me do this. So there's an assumption that I've made that lets me take the density inside the gradient. When do you get to pull things inside the gradient? Was that?
Constant.
When it's constant. So density is why? Incompressible. So incompressible means density is constant, means I can pull this stun. Plus the gradient of, I'm going to call this GP for gravitational potential, because there is absolutely no way that my handwriting can differentiate a capital phi from a lowercase phi. There's no way I'm going to not mess that up. So what is, let's talk about this grad of the potential. So the gradient of the gravitational potential, I can say that del squared of the gradient of gravitational potential is 4 pi g rho. Oh, I promised I was going to prove this. I forgot to grab that proof. I'll do this. Yell at me if I don't do this proof next time. It's a couple of vector calculus stunts that are really worth going through and seeing, because there's some interesting things where you get some divergences of stuff that turn into delta functions. And there's a couple of really valuable math stunts that go into this proof that I will just totally screw up if I try to do it. So what does this mean? So the gradient of the gravitational potential minus the gradient of the gravitational potential is the force from gravity. And that's just the same gmm over r squared, right? But now I don't have an m. That doesn't really make any sense. So talking about the gravitational force as gm squared over r squared doesn't make any sense, because now I'm just talking about some volume of fluid. This could be a tiny little bit, or it could be a huge amount. It doesn't matter. Kelvin-Helmholtz doesn't care how much fluid there is. So we have to deal with not mass, but the potential, because the potential is the continuous field that affects everything. So now the gravitational potential is a continuous field that exists everywhere, and gradients in the gravitational potential give me the acceleration due to gravity.
Wait, excuse me?
Yeah.
So that term is like what F external is that we usually neglect?
Yeah, so this is where you plug in F external.
Okay.
So in all of this, we always say that there's plus some F. That's what we're using here. So that's a good question. So we're just plugging in this force. And we can deal with this force as we like. So yeah, so what I'm going to do is use this and plug in here and use another one of these vector identity stunts that I like to turn this into, so this v dot grad v turns into 1/2 gradient of v squared plus the gradient of v cross curl v. And that second term is 0. So this term just becomes 1/2 gradient of v squared. This term turns into dv dt. So we're going to stick in, I don't want to write anything else. We're going to stick in this grad phi into all this. And then that becomes minus d by dt of grad phi plus grad 1/2 v squared plus grad p over rho plus, we got a minus here, minus, plus grad gp. So now every one of these terms has a gradient. So now the whole equation is a full derivative because every term is a full derivative. I don't have anything hanging outside of the front of any of my derivative terms. I got rid of this. So this v dot grad v, I can't integrate that guy. It's not a full derivative. But this grad v squared, I can integrate that. It's a full derivative. I'm just taking the derivative of that thing. So I just integrate, this equals 0. And I'm left with minus d by dt of phi plus v squared plus p over rho plus, okay, we're going to say that the gravitational potential is going to be g times z minus g times z. Does that work for you there? And that's going to be a plus because it's on this side of the equation. G times z equals some constant. So I just integrated, and I got this integration constant. And this thing can't depend on space, because it's constant in space. But it can depend on time, in principle. We don't necessarily need it. So we'll come back to this constant in a second. So now, what is my, so this is, now we've stated the equations. All I've done is stated what the equations are in the assumption and cooked them a little bit to make them a little bit simpler. But I haven't actually done anything real. So now what we need to do is first pick our background solution. So our background solution is v equals u prime if z is bigger than 0, and u if z is less than 0, and nothing else. I just have these two velocities, and maybe they're positive, and maybe they're negative, and maybe one of them's 0. We're just going to leave it as a generic u. This by itself is perfectly stable as long as you don't perturb it. So this is our background solution, and then our and this is constant. So you can see that this solves this equation just fine. Then we need to perturb it. So we're going to say that phi, okay, now remember phi is my velocity potential. So this is phi is just the velocity. How do I get Vx out of phi? Just take the derivative in x. So v is grad phi means that Vx equals minus d phi dx. Does that make sense? So if I need the velocity I take derivatives of phi. We'll get there in a minute. So we're going to say that phi equals minus u times x, because this is my background solution. So if Vx equals u is a constant, then phi, how do I get phi from this? You just integrate. Is going to be u times x plus your integration constant. So we can just say phi is u times x. So now my perturbed quantity, minus, because it's minus grad phi. So now my perturbed quantity, we're going to say phi is ux plus phi 1, and then phi prime is going to be minus u prime x plus phi 1 prime.
I have a question.
Yeah.
Is there like a way to physically interpret phi?
The potential function?
Yeah.
Maybe. I don't have a good answer for that. Stick that in your reading questions sometime, and I'll see if I can come up with a better answer for that. I don't have a good intuition for it, other than the intuition that I already have built up for potentials, like gravitational potential or electric potential. So it's really analogous to that. So it's just a potential that causes a velocity instead of a potential that causes a gravitational acceleration. That's maybe not as satisfying. So my velocity is going to be v plus v prime, or v1. My upper velocity is going to be phi prime plus u prime plus v1. Now I'm going to plug it into this equation. I'm going to plug both of these into this equation. And I'm left with, let's see, how did I do it in my notes? This is one of those, I like doing algebra when there's a lot of algebra or calculus. I like having the notes because I'm going to screw it up less. But I skipped this step. So I'm just going to plug these two into here. So let's start with, and we can just do, we'll just do it one time. So this becomes minus d by dt of phi 1, because this term goes away, plus 1/2 ux plus phi ux plus phi 1 plus p1 over rho naught plus g times z equals 0. And then we're going to throw out terms, which I'm going to skip. And then I'm going to wrap a couple of steps up because watching me do algebra is kind of boring. I'm just going to take this equation. I'm going to do two things. I'm going to plug in this into here. No, not into there. Into here. So we plug in this into here. We throw out all of the phi 1 squared terms. So you're going to get some of the phi 1 squared terms that come from this v squared. And then the third thing we're going to do, we're going to jump straight past doing math in real space, and we're going to just jump into Fourier space. So my d by dt goes to minus I omega, and d by dx goes to I k. Oh, I forgot. My notes are terrible. Well, past me did this in the terrible order. So we're going to do this, and then I realized we got to take a road detour. Sorry. Bad narrative flow. Okay. One of the important things we need to talk about this interface is the actual height of the interface. So we're going to call this xi. So xi is the height of the actual interface between the two liquids. So this is like the height of the ocean or whatever. So this is just the position of the actual interface between the upper fluid and the lower fluid. So I can say that dxi dt has got to equal what?
0.
No, because it might come up and down. It's got to equal v1z. It's got to equal my perturbed z velocity. Does that make sense? So the time derivative of this is just going to be the velocity of the interface of the fluid. Does that make sense? Yeah. So I can also say that this, so this I can say because that's just what the interface is going to do. But I can also say that this is equal to minus d phi 1 dz. That just comes from the definition. I can also say, I can plug in xi, I can plug in my velocity here. this is equal to sorry. That's got to be the full derivative. The full derivative of the material motion is the velocity of the motion, not the partial, because that interface doesn't have any spatial derivative. So what we can say is this is equal to d phi dt, which is equal to dc1 dt plus u dc1 dx, because this is a full derivative. But this time derivative is a full derivative. So we can equate phi and the position of the interface with each other.
I think that will still be the partial of the phi 1.
Oh yes, I'm sorry. This is a partial. This is a partial. This is a full. Thank you. So here I'm just expanding. Dc dt has got to be d phi dz because it's the velocity. It's also partial c partial t plus u partial c partial x because that's how the derivative works. Okay, so now we've taken the point of the interface and related it to phi and u.
I'm sorry, why isn't it the full derivative?
Which?
The
This? Because nabla is partial derivatives.
oh, okay.
So the phi only cares about the partial derivative, but c cares about the full derivative. There might be more answer to that question. That's a good question.
I think it's partial also, like what we're doing here is that we are looking at the interface as it is moving up and down.
Right.
And basically what we're looking at is we're looking at the fluid elements just above and below that interface. Right. Now, even though the fluid elements may move, which is why there is a partial derivative, the interface itself we're looking at from a fixed point, and we're not looking at as we go along with it, which is why it's a full derivative for the interface, but a partial derivative for the fluid point.
That makes sense. Yeah, I think that's about right. I'm not going to dwell on that too much more right now, because now we have this equation, and I'm going to take this equation and I'm going to turn it into my Fourier modes. So I'm going to say that C is going to equal. Actually, I want to start this up here. C is going to be A e to the I k x minus omega t. We're going to say that phi 1 is equal to C e to the I k x minus omega t. And phi 1 prime is going to equal C prime e to the I k x minus omega t. So now I can take this equation and this equation and combine them, and all of the phi's and x's and t's go away, and we're just left with the amplitude of the wave and omegas and k's. So then I'm left with this nice relation that says that I times minus omega plus k u prime times A equals k c prime, and I times minus omega plus k u times, well, that's going to be an A prime, A equals minus k c. So I want to do something before I go. So I'm kind of halfway through this derivation, and the derivation takes me a second, but I realize that I'm running out of time, and I want to talk about something real fast. So I'm going to jump past some of this math, and get down to, because the algebra, I screw up every time. I'm not gonna lie. This algebra takes me a minute to go through it all carefully. And I want to jump back to the results. So, does everybody have a basic idea of how we got here? So we've got these assumptions. We've got our constituent equation. We need to talk about the interface. We then do this Fourier stuff and throw out all the nonlinear terms. And then we're left with this, which doesn't look anything like our original equations, but it still has all the important things in it that are related to our original equations. That's the amplitude and the frequency in space and time. So these are the things that really matter from what I did here. So I want to jump quick to the end. You do this, you match the boundary conditions, and you do a little bit of algebra. That's really all you do. It's not super hairy from there. Setting it up and doing what I did so far is the conceptually difficult part. The rest of it is the algebraically difficult part, which I'm gonna skip. I might come back to next time. But we're left with this fantastic relation: omega over k equals rho u plus rho u prime over rho plus rho prime plus or minus g over k times rho minus rho prime over rho plus rho prime minus rho rho prime u minus u prime squared over rho plus rho prime squared. All of this is inside of a square root. So this now gives us the dispersion relation. So now we can say, if I have a two-stream instability and I perturb it, how are those perturbations going to evolve? So if I perturb it with some size, some wavelength k, what frequency response do I get out of that? Another important thing you can do is talk about when is this term bigger or less than 0? I mean, not this term. This term. What happens if this stuff in the inside is less than 0? So this term then is imaginary. So then my dispersion relation, my phase speed, omega over k, is going to be v1 plus I v2. So to remember where we stick our omega, we stick our omega into an e to the I omega t. So this will have an oscillating solution and an exponentially exploding solution. Does that make sense? So now this turns into e to the I v1t, let's put quotes around there because it's not actually right, times e to the v2t. And there's not an I here, so this one will just explode. If I put a minus sign, it'll decay, but if it's a plus sign, it'll explode. So what does this really mean? What does this really look like? So, so how many of you have seen this? Do you see a roll of paper towels in here?
There's probably one in the back.
Probably one in the back. What's that? Oh yeah, that's perfect. That's perfect. I don't want to do this with either wet or chalky in here. Because the last time I tried to do this stunt in class, I dropped the bottle and it shattered. Because I'm an idiot. So, how many of you have seen this stunt? I have. You really gotta mean it. I have this bottle of water. If I turn it upside down, what happens? The water comes out. I have this playing card. And I do this. And my playing card is a little bit bent. Oh, there you go, okay. And it stays. Why?
Is that just squeezing?
No, this is rigid. If this were flexible, this doesn't work. It fails. This has to be rigid. And the bottle has to be smaller than 35 feet. Why 35 feet? What's the significance of 35 feet? Oh, here, I should put the camera on what I'm doing.
Pressure or something.
What's that?
Maybe the pressure at that
Yeah, what is how many millimeters of mercury is atmospheric pressure?
760.
760. How many feet of water is that?
Oh, I don't know.
35.
Okay.
So a pump can only pump water up 35 feet because a pump works by having the atmospheric pressure push on everything else. So if you want to get water more than 35 feet, it's not going to work because the atmospheric pressure isn't that high. So back to this. Back to my story. So why is the water not coming out? I put this on here and it's not stuck there. I didn't glue it there. Surface, there's some cohesive forces there, but it's really very weak. So why does the water not come out?
It's kind of like sucking it up.
Nothing is sucking.
Well, it's not. It's because
The cohesive forces of the water don't matter.
air pressure.
Air pressure,
Yeah.
right. Air pressure from the bottom, so there's air pressure underneath, and I have 35 feet of water pushing up here, but only like 8 inches of water here, right? So there's a lot more force on the bottom. If that were the whole story, then when I take the card out, it will stay. You know that that's not true, right? This is fun to do in slow-mo. So what is the card doing?
This is a stronger barrier.
No.
Ensuring that it's flat. It's completely flat.
It's ensuring that it's flat. So here I have a statement about the stability of the fluid. Actually, so if I set both the top and the bottom velocity to zero, then I'm left with just, if I set the top and the bottom velocity to 0, like I had in this, then I'm left with omega over k equals g over k times rho minus rho prime over rho plus rho prime, square root of that. Let's move this k over here, and so now I get a k on top, because that's how I want it. Does that make sense? So I just took this whole monster and set u equal to 0, and we're just left with this term. So now omega prime is the density on top. So this is a strictly negative quantity. So this is a strictly imaginary quantity that depends on the square root of k. And depending on the square root of k, omega is going to depend on the square root of k. The growth rate, gamma, is going to depend on the square root of the absolute value of k. So higher numbers here, smaller wavelength. Higher k's, smaller wavelength. Grow faster, right? So when I have the card on the bottom, but every k, there are no k's that I can plug into this equation that make this not imaginary. Every wavelength is unstable. So when I put the card on the bottom, I make it perfectly flat and I suppress every wavelength. As soon as the card is gone, then I have perturbations to some wave. It doesn't matter. How I pull the card off dictates how the instability grows. But as soon as I take the card off, then it is Rayleigh-Taylor unstable and it falls out. But the card does two things. Pressure pushes it up, but the card suppresses the Rayleigh-Taylor instability, and that's why it's important. Yeah.
If you could somehow put the card there and then just make it like despawn instantaneously, would it still like would those perturbations spontaneously form, or
Yes.
Okay.
So I went to this summer school when I was in grad school that was all about fluid turbulence, and it was really fun. Because the Cambridge Fluid Dynamics Lab is like Disneyland for fluid dynamics experience, which sounds really stupid, but I'm a giant nerd. So I'm going to take the last couple of minutes and just show you. So that's an interesting question. So if you want to actually measure the Rayleigh-Taylor growth rate, especially, so this is good for the linear regime when these perturbations are small. That is not what you witness when the water comes out of the bottle. That's large. That's a large growth rate, yeah.
Could you create like an airflow that's strong enough to keep the water pressure like, over there as well?
And no, because it is unconditionally unstable. I saw this, so there's a whole genre of design called flawsome, which sounds awesome, but there's a deep flaw in it. I saw a patent application or a design for an umbrella that works just by spraying a hard jet of air upwards, and that just won't work ever at all because it's Rayleigh-Taylor unstable. It is unconditionally unstable to all wavelengths. So there is no way to build an air cushion that will keep air up. It will always come through. And that's what this says. Let's look at some experiments here. Oh, right, I can't see that anymore. So I saw this. I went to this cool summer school, and they had several examples of how to actually do Rayleigh-Taylor in the lab, and I'll show you one of them. Oh, where is it? Kelvin. Here. You come up on the wrong side. You came up on the wrong side. So this is upside down. So what happens is, what's going on in this video is there's a tank of water and a barrier above the water. On the top half of the barrier is salty water that's colored green, and on the bottom half is natural water. They slide the barrier away and then watch the Rayleigh-Taylor develop. Oh, there's music even. Huh. I forgot about that. Normally I zip past this part, I think. So here he goes. Here's the barrier coming. And you can see the perturbation is seeded by this barrier moving past. And then you can watch the linear growth and then the nonlinear growth as these bubbles all mix and form and combine. So this is a pretty common way to do these kinds of experiments, is to have a barrier that you can slide out carefully and smoothly and fast. And then there's more details, and they go through other ones. Let's see. I know. I know. So anyway, so this is.
I'm pretty sure you can also do it with like two bottles of the same mouth with different. Because I think I've seen that where they have that, and then they put a card in the middle, and then they slide it, and it also shows the RT instability.
So one of the cool experiments that I saw at the summer school was a similar thing, except they do this in the Arizona Fluid Dynamics group. They have a tank with salt water on the bottom and neutral water on the top, and they put it on the top of a very tall tower. And then on the top of the tank, they put rockets, and they fire it at the ground really fucking fast. And this is just G. G is an acceleration. It doesn't care that that's gravity or just some other acceleration. And this forms perfectly. So you can see these plumes form. If you do it really carefully, they form this really classic cartoon structure. So, so here, this is our first perturbation. And this is heavy fluid and light fluid. So our first perturbation starts to drop like that. And then there's a shear instability. And you can see these other instabilities roll up along the side, and then it starts to mix. So this is what the canonical Rayleigh-Taylor fluid looks like. Rayleigh-Taylor is heavy on the top and light on the bottom. And it tends to form spikes that go down and bubbles that rise up. This one also shows a lot of the Kelvin-Helmholtz instability. The Kelvin-Helmholtz instability is the shear instability. And if you take this and leave one of the velocities, you take this dispersion relation and you set one of the velocities to something that's not zero, then you'll see the growth of the Kelvin-Helmholtz instability. Kelvin- Helmholtz instability is two different densities of fluid. So here's a simulation of it. So now this fluid, I have two slightly different densities. It doesn't matter which one. So here we usually do the heavy one on the bottom. Actually, there's no acceleration in the vertical direction, so it doesn't really matter. And there's a shear relative to these two things. And you see it starts to grow. And this also has a grid perturbation on it. So these little perturbations grow, but you'll see that this will start to get hooked up and, oops, it goes the other way, hooked up and dragged into, oh, I thought this was a Kelvin-Helmholtz. This is another Rayleigh-Taylor instability. This is just really slow and pretty. But as these two fluids are shearing past each other, that is also another instability, just like what we just derived. That's not the video that I wanted. It is a cool video, but I wanted to show this one. So here, here what we've done, we've got the red stuff is a salty solution. So, oh man, they're closing GFDI, which is the Geophysical Fluid Dynamics Institute that used to be in the basement of the physics department, and they had all of these demos that we could do. So we did this in fluid dynamics when I first started here because there was experiments that we could do, but unfortunately GFDI is not thriving anymore. So this is a long tube, and there's fresh water and salt water, and what they're going to do is very slowly tip it so that the salt water, which is heavier, is going to slide this way, and you'll have a shear instability between the two sides.
This experiment is called the Kelvin-Helmholtz instability of a shear layer between the two layers.
How do I show you up?
Begins with a clear layer of fresh water on top of the denser red dyed layer of salty water in a long horizontal tank. To set up this experiment, the empty tank is tilted and then half filled with fresh water.
And then they have fill it with that, and then they very, very slowly prop it up. So they very slowly down like this, and now the shear happens. You can watch.
And thus shear is generated between the two layers. Suddenly, the interface between them
Then it
becomes
gets
unstable.
To this classic rolling kind of shape.
Let's watch that again closer up. Remember, the lower dyed layer is flowing to the left, while the clear layer flows to the right.
So you just have some natural noise that seeds the instability. So whatever garbage happened when you moved it seeds the actual instability. I talked to it.
Keep your eyes open. You'll see interesting flows like this.
But this is a
around
great.
you.
Here it's not as noticeable. But I lived in New Mexico, and I would see this Kelvin-Helmholtz in the clouds a couple of times a year. Not regular. The conditions have to be pretty smooth. Okay, that is all I have time for today. Is there anything else actual crucial that I needed to talk about? No. I want to talk about all those